because of time constraint. I've been very busy, and it's likely going to be very difficult to come up with appropriate timing for this every week. So I have compressed everything that we will need in this session. So I urge you to pay attention and stick closely as we proceed. So I was about talking about the disadvantage of being a process engineer. There are so many advantages. Of course, you make a lot of money depending on what level you are in the industry, and it's almost a predictable pathway that you continue to rise in the industry as long as you have gotten into the industry. So that being said, the disadvantage would be that if you start in the oil and gas, for example, and you find an opportunity advertised somewhere online or on LinkedIn for process engineer in the food and beverage industry or in the pharmaceutical industry, it might be difficult for you to move from the oil and gas to either of these difficult industries. It's not impossible, but it's a process engineer who started or who had been in the food and beverage will be considered first before you coming from an oil and gas. So the same applies to someone, a process engineer going from food and beverage industry to the oil and gas, as well as pharmaceutical to the oil and gas. So because these processes are kind of different. For the pharmaceutical, it's usually a batch process where you have to produce drugs and they produce today and they are done for the day. But for oil and gas, it's a continuous process. Okay, which is also different from the food and beverage industry, where you produce the biscuits, the cereals, and the rest of them, and also the beers and the drinks, the Coca-Cola, and the rest of them. So, if you know you are interested in either of this field, either you prepare yourself to move into all fields or you stick to one. And also, I want to say this quickly, just in case you've been preparing yourself to get into this field and you're not able to find employment for one reason or the other, it's advisable to also go for a master's degree. If you have a bachelor's or if you have your HND, go for a master's degree in this field, and it will give you more chances to get into the process engineering. It's actually considered an advantage. Then if you don't find employment at the master's level, you can go for a PhD level, which will give you a broad exposure to a lot of things and prepare you for consultancy or research and development in the process industry. So these are the pathways you can go. So let me go to this diagram very quickly. I hope everyone is here, present. We check. Okay. All right. So we are present. So this is an overview of the oil and gas. I'm focusing on the oil and gas because this is the area where I've been exposed to. And at the beginning here, you find a multi-phase field from production well heads, which would be a mixture of oil, sand, mud, and lots of things and water. So after the first stage, you have the inlet manifold. This manifold will be receiving from several wells. So and then it goes into a separator, a three-phase separator most of the time because you will have three phases. You have uh, oil, gas, and water in this uh, area. So at the top you have. Oh, I promise that I'm going to explain to you the concept of three-phase separator. If we have time, we'll go through it. But if we don't have time, you should read up on your own because it's one of the very important equipments in the industry. Okay, so you have a three-phase separator here, which will separate the water and between water and oil. Uh, Between water and oil, one is denser than the other. So one will settle at the bottom, the other will be at the top, and of course, gas, which is lighter, will be at the top. So you have this three-phase separator separating into one, two, three phases. So you have water going at the bottom, and then you have another industry here, which will be treating water, the water from this stream from the three-phase separator at the bottom. So you have the effluent water treatment, then you have the effluent water storage, and of course, pumping and whatever, injecting back to the wells. So, and the other stream here, we have the desalter streams that will remove the salt from the salt content of the crude oil or the feedstock to prevent fouling of the downstream equipment because it will cause um, formation of acids in the downstream equipment, which could cause or which could lead to corrosion in the downstream equipment. So now that I just mentioned corrosion, I have to remember also the corrosion engineers are also important in this industry because they have a role during the development stage, during the design stage. They have a role to play to advise on what type of equipment to use or whether carbon steel and also the rating of the equipment, the thickness of the equipment, and also they will decide the lifespan of the equipment. For example, for vessels and pipelines, they have different lifespan. It's more expensive to replace a vessel like this, like a three-phase separator. So if you want to design this, you have to use a very suitable material that will handle the corrosion and corrosivity in the from the feed that you'll be handling. But for piping systems, you can easily replace a pipe spool by just you can replace it today and you continue operation the same day. But for process equipment, it takes longer time. So the time can be translated to the cost and also the cost of the equipment also. So all of these are also considered during the design. Why are we saying all of this? Because they are important to consider before you start your design. You don't just go and start a design without considering all of this. And at the end of the day, you deliver the documents and then the contractors starts the projects and start the construction of the project and at the end of the day find out that what has been designed will cause a lot of problems or will lead to losses and eventually probably the break-even point of the plant will be longer than expected and this business might crash. So we do not want this. So this is a very careful and very delicate stage. So going through all this process and we pipe in our we pipe or the industry or the plant is able to provide high quality food with less contaminants through pipeline or through whatever a vessel or through pipeline to another facility. And then the top part, which is the gas, so it goes to compression trains where the gases will be treated. So the gas will be treated at the gas sweetening unit. The gas sweetening unit is where you remove the CO2 and sulfur contents of the gas, and as well the hydration units where you dehydrate the gas. And there is actually more to this. This is just a simple block diagram to just give an overview. There are more to this. There are more to all of this. So, and the dehydration units, like I said, remove the moisture content up to the required quality level, and of course metering and export. This metering and export will depend whether it will be metered in gaseous phase, or it will be metered in liquid phase. That's CNG, compressed natural gas, that's gaseous phase, or liquefied natural gas, liquid phase. So both will require different processing. So so that being said, now let's go to the next thing because we will be in this session. We will try to be as fast and efficient as possible to ensure that you receive every information that you need for this. Okay, so going forward now, it's important to know the types of chemical engineering operations or process engineering operations that you will be designing. This is very important because uh, it will help you to decide what type of equipment you will need in each unit and what type of and also other considerations you need to apply to ensure that you have a proper design that will meet your clients' needs. So this you might already know, but this will be a reminder for you. So we have the unit operations, which are physical changes, which is momentum transfer, which is just a transfer from one point to another, no chemical reaction going on. Then you have heat transfer, transfer of heat from one medium to another medium. And you have the mass transfer, which is also transfer of components, which could be, for example, if uh, you have a mixture of natural gas, and you're transferring this uh, all the components from one point to another, and it goes through a separator, for example, like a three-phase separator that we saw here. The mass stream will be divided into different streams, of which what will be and this at this bottom stream will be different from what will be at this other stream and what will be here. So you have more vapor in this stream, and you have of course oil in this stream, and you have water in this stream. So this is your mass transfer. So transfer of masses of the component. So the components going here, going through this path, is not the same as the component going through this path. Of course, the components going through this path are the same while they're going through their processes or processing. So this is different from momentum transfer. Momentum transfer is just the transfer of the fluid from this point to this point to this point and to the other points. While the mass transfer is the transfer of the components. So of course the heat transfer where you require exchange of heat from a heater or a cooler or whatever. So now do we have the unit processes, which is reaction or synthesis. So which can be catalytic or non-catalytic, in depending on which process that you are designing or the scope of your design. So this is a very common interview question, just in case you apply for a job and it's an entry level job. This question is mostly asked during the interview. So it's good to note this. If you do not remember this, it's good to remember this when preparing for your interviews. Okay, so now let's try to see if we can, let's do a little exercise before we go further to the next thing we are going to do. And we are going to try to differentiate between unit operations and unit processes. It's important that we understand this before we go forward to drawing and simulating and all of those technical things. So, so yeah, before I go ahead, before I will approve of you to unmute your mic, someone's mic is unmuted, please. Okay. So, before we do that, because I'm going to require us to unmute our mic at some point, but not now. So first, I want us to look at this process, and we can see here 40 grams of olive oil. We can see 7 grams of yeast, 500 grams of flour, 3 grams of salt, and 275 grams of water, all going into a mixer. And then goes through mixing, and then what comes out here is about 975 grams of dough. So if we look carefully into this, we'll see that everything that goes in here is the output. So input is equal to output. That's your mass balance. Okay. So now the question that I have for you, where I require you to, I think it's better we put it in the chat box because it will be chaotic to have everyone on their mics. So the question will be, is this a unit operation or a unit process? So please type in the chat box. I need everybody to type in your responses, and while I will check your responses on the chat box. Okay, I have 5 responses saying unit operation. If there is any other person who doesn't agree with this, okay. So it seems everyone agrees that it's a unit operation. All right. So now this is a process for bread production. So I like to use very simple processes before we go into things that are more complex. So this is a simple bread production, right? For example, let's say a bakery. Yeah. And then they're mixing all of this, and then at the end you have a dough. Now, would this be the final step? Yes, it's possible to be the final step, or it's possible to have a more a more detailed and for a better product. There will be another step that will be required, and that will lead me to one question. During bread production, you have these components. Do you think do you think a reaction will occur in this mixer? Look at the components carefully before you answer. Do you understand the question? Is my mic muted? Okay. Okay. Yes. The question is looking at the input, the feeds to this mixer. Okay. Someone says the reaction will occur. Okay. And what reaction would that be? What do you think would be the reaction? Thank you very much. Yeast and flour. Yeast and flour. Yes. Which will lead to the production of CO2 and ethanol that will give the dough a flavor and also make it to rise. So in that case, if you have a unit, you can have a unit process with unit operations involved. So the reaction occurs in this one. So what will you call this is a unit process? Yes, there are unit operations going on, which is the mixing of the other ingredients. Yes, that's the mixing, but then a reaction goes off. That's why you have this reactor here. So the dough is reacted, and then you have a bread. So this is a representation. Of course, everything goes on in the mixer. Everything goes on in the mixer, and then you apply heat to it, and that's it. You have your dough. So, but this is a representation of what's going on. These two diagrams gives you like uh an idea of what your response would be. So it's a unit process because there's a reaction that took place in the process of producing this bread. Okay. So and this is what separates the quality of the bread you have from the bakery. Some breads are more expensive than the other because some had a very quick production where in place of yeast or for very little amount of yeast, they had more baking soda. They have more baking soda to make the dough to rise. So yeah, so that's part of what makes. Uh, okay, I have a question. Just hold on a bit. So that's what separates the much more high quality bread to the other breads that have that were produced via baking soda. Yes. Okay. So, what will be the question from who raised the hand before? Shahima, I think. Okay, Shaima, please unmute your mic and next question.
Hello, good evening, sir. Please, I can you could you please come again? I don't get it about the mixer. Will there be any reaction in the mixer? Because I'm doubting if there will be any reaction in the mixer. And if there is a reaction in the mixer, what reaction? Because I know this is operation for the mixer and unit process for the reactor. And here for the mixer, there will not be any chemical change, but for the reactor, there will be a chemical change. So I want to know, maybe this one is quite explicit. So please clarify this for me.
Okay, thank you very much for your question, Shaima. Okay, so because this process sometimes is a crude process, it's not like it's not a refined process in most bakeries or, for example, in fast food restaurants. They this could be your final representation of what's going on in the process. This is like a summary of what's going on in the process, the mixing, the the baking, everything, the panning, and all of it. Everything goes on in this process, and then you have the final product, which is a dough, which is your dough, and your dough gets heated up, and then you have the bread. Okay. Okay. I think I'm explaining this the wrong way. Because yeah, I think you're right. You're right because it's when you apply the heat that is when you have the reactions going on, the yeast and everything. So it's in the reaction step. That's when you have the bread. So, but what I was trying to say is that the entire process of the bread production is called a unit process. Okay, sorry. The entire process of bread production is a unit process. So, if you'll be asked the question, is bread production a unit process or a unit operation? The answer would be is a unit process. And in that unit process, there are unit operations. I don't know if you understand. No. Did I explain it very well for you to understand?
Yeah, now I get it that for bread production it's a unit process because it involves the reaction because there are a lot of other things that will go on, but mainly it's going to be with the reactor. Thank you.
You're welcome. Okay. So last that being said, let's go to the thing we have. And yes, what softwares will we require for this? So we're going to require Aspen Suite, Aspen HYSYS, Aspen Plus, Pro 2, Pro Max, DWSIM Pro. These ones are professional softwares and you need licensing for them. They cost a lot, from $2,000 per year upwards for individual. And it costs more for organizational license. So, but for educational purposes, we will use DWSIM because it's open. But DWSIM has limitations. uh, Except you pay for the pro and then you get to have full flexibility with the app. You get approximate the same utility with the Aspen Suite. So this will be for the simulation, and for the PFD and the P&ID would be AutoCAD Plant 3D. However, this also requires licensing, which costs so much. So I do not know if your schools or your universities or institutions have the educational license for these softwares. So if you do not know, you should ask the study coordinators or probably the person responsible for your ICT or technology. They should be aware if you have licensing for this, where it will just require you to use your school email and create an account on the website, and you will be able to download the professional suite of these, but it will be available for you maximum maybe the period of study or for 1 year. This is usually the strategy. So, but for this session, we will be using DWSIM and draw.io. I don't know if you are using your laptop for this session. If you're not using your laptop, you might want to use, or you can just watch the recording later if you don't have your laptop, and you repeat the steps that we will follow this this lesson. Okay, so first I want to know how many people are using their laptop. Please, can you drop it on the chat box if you're using your laptop tonight? Drop it on the chat box if you're using a laptop. I need to know how many people. Okay, we have Marshall using a laptop. Okay, so we have a few people using the laptop and others are using the phone. Okay, so if you have used the DWSIM before, please can you indicate also if you've used the DWSIM? You have some knowledge, or you have some knowledge of Aspen ISIS in the past or recent. Drop it in the chat box. And also, if you have used AutoCAD Plant 3D in the past, also. Okay, so some of us have been exposed to these two softwares, and who has a licensed version, or who has a, okay, I don't want to say cracked version. So this who has a licensed version, because cracking is theft, and we are live online, so should be careful. So who has a licensed version? Okay, from school, and you have access to Plant 3D. Do you, Shahima, or just the AutoCAD? Uh, because the suit I think is more applicable to civil, and then you have electrical, and then you have Plant 3D. Okay, so if we do not have Aspen Hysys installed, please can we download DWSIM? If you already have DWSIM, drop in the chat box that you already have it. And if you don't have it, you can download it on the internet. It's open source, and it's easy to install. Just follow the prompt and you get the installation done in no time. And draw.io is an app also, it's a software. However, you can use it on the web. You don't need to download it. You can use it directly on the web to do your drawings and your designs, and the rest of them. Do I have a response for people who have installed the DWSIM? If you have installed it, please drop something on the chat box that you have installed DWSIM. Or if you are installing or in the process, just drop it on the chat box so that I can know what you're doing. We need to communicate, and please use the chat box for communication. It's very important. Don't be shy. Just use the chat box. It's for you. Okay, you have Unisim and analysis. Okay. Okay, so Shaima is she has the privilege of Unisim analysis already set up for her. So those that don't have the Unisim analysis, just take advantage of DWSIM. Okay, your analysis. Yes. Okay, so while we're doing the installations, uh, the first one we're going to use is draw.io anyway, and you don't need to install it. You can just go to the website, draw.io, and you will find. Okay, do you want the link for DWSIM or draw.io? Okay, I will drop the link for both of them. And if you use Windows or Linux, there the software is available for both Windows and Linux. Oh, it's impossible to download it from using the phone. So we have links for the Windows and Linux. It's both are available there. Uh, sorry, Windows and Mac OS. Windows and Mac OS. Yeah, and also Linux. Yeah. So three of them are available if you depending on which system you're using. And draw.io, draw.io, draw.io. Uh, so while we're doing the installation, we will start with the concept of the design we will be doing, and we're going to choose a very simple concept. So first, it starts from coming up with a scenario, what you have in mind. Maybe you want to design a plan for bread production. Of course, this is solid. You know what equipment you need. You don't require a separator here because, of course, you're not separating anything. You're rather mixing. So that's just the that's just the concept of the study. So you define the design basis, the objectives of the project, and your objective will be what you want to do. What do I want to do? Do I want to start processing or producing beer, or do I want to produce Coca-Cola, or do I want to produce drugs, or do I want to produce kerosene, gas, methane, and other petroleum products. So first is to define concept. What do we want to do? So that helps to define the basis of the design, what we want to do. Okay. So going back to this part, um, yes, and also before I go back there, your feedstock specifications. What's the specification of your feedstock? The conditions and composition of your feedstock will also determine what kind of equipment that you will design, kind of equipment you're going to include in your design. So the feed conditions are very important. What are the conditions you receive the feed, and what's their composition? Okay, so going back to this diagram here, for example, you have a well, and these wells have different compositions. Over here, you have sulfur, here has CO2, or here has both sulfur and CO2. That will decide what kind of equipment you're going to have downstream the of the feed inlet. Okay, so that is very, very important. For example, if you have uh, more paraffinic crude, or if you have more naphthenic crude that have the ring structure, uh, the design of your plant will be different from that of crude. And of course, the naphthenic would cost more to process than the paraffinic crude. So all of these are important to determine during the concept of your study. So and then when you have determined all of this, there are other things I didn't include in this session because it's impossible to go through. Excuse me, to go through everything that will help us uh, to go through this process because this, like I said, this usually happens in a project team where different professionals are handling different sections and different deliverables. So then you go into the development of the studies and the basic engineering package, where you have your PFD, your BFD, then you develop your BFD into PFD, then you develop your PFD into your P and ID. So for this mentorship, the P and ID will be impossible to develop because we will be using a very simple system for it, but it will be impossible to develop because a lot of things are considered and the sizing of the line, the sizing of the equipment, and all of those things, the controls. So the controls are required, and this scope does not cover uh, the controls of the equipment because the controls of the equipment will require uh, automation and this is another branch of process engineering. So which I am still learning in this field also. So yeah, so note that we will not go into controls. However, we might touch just a bit of it, just a bit. All right. So the deliverables will be the equipment and systems for procurement, because after you've done the design, and of course, from one stage to another, there are lots of meetings that have to go on, the hazard studies, and the analysis for the risk and everything, and the safety considerations, safety meetings, and all of that before, and several reviews of the documents, several reviews of the PFD, and because this is very, very important. The project usually costs billions of dollars, so you have to ensure there are no mistakes. So all stakeholders will be involved in the meeting. So it's very important to know this, that it's not just the technical aspects, because anybody can learn the technical, but the soft part, soft skill, the attendance of the meeting, the discussions, and what to discuss, what's important to discuss. They show that you are a good process engineer. When you focus too much on the technicals, although learning from the technicals will also help you to build the soft skills, where you go into discussions and meetings uh, with other project teams. Okay, so Okay, so after the design, when where we have the deliverables, we are now sure that okay, this plant will be successful. We go into the construction of the plant, where and then finally to the commissioning and the operation of the plant. So this is where the plant is now started running, and the plant now goes towards the point of breaking even. Another thing that was not that's not listed here is in the design scope would be is the over design and also the minimum operating condition. Usually you have to usually the practice is around 10% over design of the plant, 10 to 20% over design of the plant, and this is to allow for increased production. Okay, and also the lower limit will probably be 50% of production. That's to say that, for example, if this plant is going to run, this is a different plant, this is a different plant, this is a different plant. If this is going to run, if we are going to have very, very successful days of production, we should have at least above 10%. Like the plant should be designed to accommodate a 10% increase in production from the design production rate. Then also if it will go lower, probably 15 to 50%. And when it goes below this, the plant is not making, it doesn't make sense to run the plant. So to be advisable to shut down the plant. So all of these goes into the, what you call the philosophy, plant philosophy. So these are not mentioned in this training session because it's impossible to cover all of it. And then, of course, the utilities and supporting systems. These will be your instrument air, your nitrogen systems for blanketing in the vessels, instrument air for controlling your instruments, uh, opening and closing, and also actuating. In fact, actuating of the instrument. So you need instrument air. And you require electrical signals as well to be able to translate them from pneumatic signals to pneumatic electrical to pneumatic signals. They call them I2P. Okay, so these are not covered in this session, but it's good that you know it and you are aware that you need to send electrical signals from the control room, and then the electrical signals will be translated from either digital or analog signals to pneumatic signals. Okay, so this is not covered in this session as well. So there are things you can read up, but if you have questions in these sessions, feel free to send them maybe on the WhatsApp group at the end of the session, and then we can have a separate discussion on this. Okay. So now, all right. So going to the concept of this study, and we have to define the design basis, and for this uh for the sake of this mentorship and for the sake of the limited time that we have, I have to apologize for my end because I have very limited time for this. So I have chosen a very simple process for this, and it's going to be the utility aspect of the plant, this part. Okay, it is very, very important. Without the utility, all these cannot function because the utility will supply the water, the cooling water that you need to cool any unit, to supply the heat that you need to heat any unit. For example, if this crude oil will be fractionated, you need heat on the fractionating coolant. The utility will supply this. Okay, through okay, this is another deep concept that we are not going into, but it's important that you know it, that you require systems like hot oil systems, and which will help in generating the heat for the fractionation. Okay, so yeah, back to where we were. So we will generate steam for the process for heating and electricity supply. and that's what we're gonna do here. And for steam generation, uh, give me a moment. Okay, I think that's fine. We can do it. All right, fine. For steam generation, what what is the feedstock or what are the feedstocks you would need to generate steam? If you have an idea, drop it in the chat box. Okay, water. Shaima said water. Okay, so if you will need water as the feed, uh, what are the equipments you will need to generate this steam? Okay, only one person is responding on the group on the chat. Generators, boilers. Okay, reboiler. Okay, so uh, to generate steam, we're going to need heat. We need a heat source, and we can get the heat source from boilers. We can get them from boilers. So for reboilers are actually more for your columns. They're more for, yeah, for your columns. So the reboiler is attached to the column for generation of heat. So what you will need is the boilers. The boilers. So and the boiler is a heater. Is a heater. It's classified under heat exchange. So last time we went through some of the symbols of the process equipment, and we will likely be seeing them again today because we'll be using them. So we'll need boilers. What other thing do you think we'd need? If we have a boiler, we have the feed water, turbine. Okay, so what will the turbine be used for? Okay, Shahima, go ahead.
Please come again with a question.
Okay, yeah, you all have been mentioning the equipment that you need. We have established that boilers will be used for uh, converting the feed water to steam, and then Oguche Moses said we'll need a turbine. So what will the turbine be used for steam
Okay,
generation?
I don't know that the turbine. What I know is that I used to generate steam. Like when you put water in the turbine, then it's how do I say a turbine and a compressor. So the turbine will heat. Actually, I don't have much idea on it, but I know the turbine will generate steam in is this spray form?
Okay, in spray form. Hmm. Okay. Good Moses, please unmute your mic and thank you, Shaima, but not quite. Let me hear what Oguchi Moses wants to say. He says turbine to pump the steam. So, can you tell us how this turbine will pump the steam? Please unmute your mic.
Oh, okay. Good evening, everyone. I think the turbine work like a compressor, but it just uses steam instead of maybe gas as the feed. So it uses steam. So it just works like a compressor to pump in the steam in.
Okay. Okay. It uses the compressor to pump the steam. Hmm. Okay. So the okay now the turbine will it uh mm, will it take the steam, or will it is it going to take the water and generate steam, or is it going to take the steam? Do you understand my question? Okay, Shaima, go ahead.
Please, you can come up with
Sorry, I didn't hear you, Shaima.
um. Could you please come up with a question again?
Okay. Uh, we are trying to establish if the turbine you are talking about will use the steam or generate the steam.
Okay, so I know that the turbine will use the steam because
Okay.
it will use the steam to generate power. Or
Okay.
yes, so that's why we always say it's exothermic because it's like it's doing work to the surrounding. So it's
Okay.
now using the this thing to the surrounding to generate power.
Okay. Thank you very much. So now let's explain this clearly now. So I hope everyone is paying attention. The turbine, there are different types of turbine, right? Okay. Now, the turbine we are talking about here is the steam turbine. We have the gas turbine, which will combust gas, natural gas, whether methane, propane, or whichever one the gas turbine was designed for. Then we have the steam turbine, which will take steam. The steam is what's going to turn on the blade of the turbine. While the gas turbine will have uh, combustion of natural gas in the casing of the gas turbine. So these are two different things. And what they do is they take this steam and convert this potential energy from the motion of the steam and the gas into a mechanical energy on the shaft. And the shaft is connected to a generator. I wish I had an image to explain this, but unfortunately, no. I need you to just think about it, imagine it. You have the turbine, and then the shaft of the turbine is rotating as it's connected to a generator. The generator now generates electricity. So that's what the turbine is for. But there is another type of turbine, which is it's called a hydraulic turbine. This has a completely different operation. It does not generate electricity. It doesn't generate electricity. It receives liquid. It's called a hydraulic turbine. It receives liquid that has a very high uh, from an overhead source. So the kinetic energy of the fluid flowing into the hydraulic turbine rotates the turbine blades, and then as it rotates, this is functioning like a pump. The hydraulic turbine is basically a pump. It's basically a prime mover, not a pump. So it's connected, the shaft is connected to a pump, and then it rotates the shaft of the pump, and then the pump is able to pump liquid. So for a hydraulic turbine and, and pump configuration is similar to electric motor and pump connected via one shaft. Why the I think I'm supposed to be writing this so that you can let me see. But I don't know if you understand what I'm saying here, or is there confusion? Do you all understand? Please, I need you to communicate, respond in the chat box if you do understand. So, this is a hydraulic turbine. A hydraulic turbine will receive fluid, which is liquid, and this liquid is going to rotate here, and the shaft will rotate and is connected to a pump. And so the liquid has energy, comes with some energy, and then it goes here it goes out with the spent energy. The energy is spent here. So the energy here will be higher than the energy here. So it uses it to rotate the pump. There's a pump. Okay. But for the steam turbine requires steam. Requires steam. It takes steam, steam goes in, and steam goes out. Of course, the steam will probably go at a higher temperature and then come out at a lower temperature. And then this is connected to the shaft of a generator that will supply electricity. Standard symbol for electricity. So that's it. So either steam or gas. Why this one will be a motor connected to the shaft of pump. Okay, so I will clean this. I hope you got that. So going back to what we were saying. Okay. So now we have said that we need these equipment. We need the excuse me heater. We need the boiler. Yes. And for electricity, we need the turbine because we have established that we need the turbine for what electricity. Because the steam turbine is what will be able to use the steam, convert the steam's potential energy to um, mechanical energy. Yeah, so mechanical energy. The turbine itself does not generate the electricity directly. It's connected to the shaft of a generator. So yeah. Okay, so now let's go to. So we're going to design this. We're going to design this, and the feed specification has been defined for you already. The feed specification will be 30 degrees. It will be almost at ambient temperature, and we want the pressure to be uh, 10 bar and 300 °C. Okay, so this is what we need. These are the information we need for now. We have already answered this question, which equipment will require. So we'll develop the BFD and the PFD for this. So before I go to the next thing we have, so let's quickly go to, let's try to develop develop the BFD. It will be very fast with that. So now this is draw.io, which I already told you to that you can use this this application. Although it doesn't replace AutoCAD P&ID, doesn't replace AutoCAD P&ID, but for educational purposes, we can use it and learn. Okay, so if you've seen it, all you just need to do go to draw.io, drawio.com, and then you click start. You don't need to download, just click start. It doesn't require login or registration. So that's why I love this. It's very easy to use. Okay, I think I shared it before in the group, but I'll share it again. So this is draw.io, drawio.com. So to skip all the requirements for AutoCAD P&ID, trying to get a license for it, running around the internet to download. I know most engineers have this stress. You go to different chat groups and ask questions. Oh, who has AutoCAD P&ID software? Who has AutoCAD Plan 3D software and all of that? The same with Aspen. So it's actually stressful. Aspen used to have educational version, but after a while, to maximize their profit, they started changing these things, and so schools have to pay for license for these things to be able to access it. So all you just need to do is click start and opens, and let's wait for the script to pass. And okay, please don't worry about this one. We're gonna do something fresh. So I'm gonna cancel this. We're gonna do something from the start. So yes. So if you have this, you're gonna see this. It has file, edit, view, arrange, extras, and the rest of them. So if you have opened this, please drop on the chat box that you have opened this. You see this on your draw IO. If you're using mobile phone, I think you can also see this, but of course your screen is small and it will be super difficult for you to replicate whatever we're doing here. So it's better to use your PC for this. So now, before going ahead with the drawings, I need to sound a note for you to take, and this will be that before before drawing is not just picking the drawings and just making the drawings, because anybody can just pick the drawings and make the drawings. Lots of meetings have to go into considerations, why we have to choose this equipment, why do we choose it, and this was part of what we just did. We just had a meeting and we decided from the concept that we want to generate steam that we will need boiler. We agreed that we will need boiler. So this was the meeting. This was the different project teams. We had the meeting and we decided we need a boiler and that we will need turbine for generation of electricity. Okay, so now you will see here on this path, you will see general, mix, advanced, or whatever. So I'm not sure you see process engineering. I'm not sure you have this tab on your sidebar. If you do, please just let me know in the chat box. If you don't, all you just need to do is go to more shapes. You go to more shapes and you see more shapes. You see general, and somewhere you will find the process engineering under order. Go to order, you find electrical if you want to do electrical stuff. So for those who are into electrical engineering or those who are interested, because as uh as an engineer, you are not limited to learning just one thing. You can expose yourself to other things. Like I already said before, another aspect of process engineering is process automation engineering, and you require this skill if you want to be in that area. So of course, logic gates, diodes, triodes, resistors, and the rest of them. and you need them if you want to go into control and instrumentation. So, but for process engineering, this is what you need the symbols for the valves and the rest of them, the pumps, compressors, and yeah, basically that. Then of course the engines, the motors, or whatever. So feeders and stuff. So if you have this, and of course the instruments, which I said we will not be going into P&ID because we require the instruments for the P&ID. Okay, so that's it. So if you have attached this to your sheet, please uh, drop a P on the chat box. Drop a P. Let me know that you already done attached to process engineering. If you're on tickets, you don't have. If you tickets, you have it. So everything you pick is what you will have. So yeah, okay. So most of us, I think some of us have done it, and then that's it. So for your AutoCAD P and ID, it's quite similar to this, and on each bar you have the equipment, the valves, and all of that, all those symbols that we went through, the control valves, of course. So yeah, we have all of this, and now let's start the design. Let's start the design. So we said we need the. So what will be the first thing to drop on this? Now we want to skip the BFD and go straight to PFD. What will be the first equipment to add here? If you know, please drop it on the chat box. Be the first equipment. Okay, this one yours is loading. It could be your network. Maybe you will need to download it if you have network issues. So because we are all working on the web, this is a cloud service. Okay, Ben, please can you unmute your mic and say what you mean by description, equipment, shape?
All right, sir. Good evening, sir. Yeah, what I was trying to say is that the shape, the actual equipment, just whatever one wants to put, just like indicates that shape, something like that.
Okay, yeah. So yeah, that's it. Thank you very much. So that's what we'll need. We'll need the equipment and yeah, we need the equipment. But we also need the source of the source. So we need the input to the equipment, which will be the feed, right? So Desmos still has issues. JavaScript, please ensure JavaScript is enabled. Desmond, I don't know which browser you are using. Maybe you want to use Chrome or Brave browser. So I recommend you use Chrome or Brave browser for a smoother uh, utility. Okay, so yes, so we said we need the equipment, and so which equipment should we drop here? Which equipment do we need to drop here? We said boiler. So we said boiler, and boiler should be classified under heat exchangers because you're heating water and water is being converted to. So boiler will be under heat exchanger. Okay, so let's look for boiler here. We should find boiler. And okay, we have electric heater. So electric heater here will be very expensive to use. So this is a heater. We can use heater in place of a boiler. So we can drag and drop it, and that will be our heater, which is our boiler. Okay, so we need to have a label for this, and the label would be, let's go to flowchart, arrows. We need the line and we need the arrow. So another important thing, we need to specify battery limit. I don't know if I explained. I think I did. I explained battery limit in the last one of the sessions we had. So we need to we need to specify the battery limit. So first we need to add a line, and where is the line? Should be on basic line with label. Okay, this we use this to specify our battery limit. So this is to show the beginning of the plant, right? This is the beginning of the plant. Okay, so we need the line. No, I can't find the line here. Okay, yes, that's it. So you find the line on the general. It's not on the basic. And the line you will need will be the one with the label. Okay, the one with the label is what you will need. So we pick it here and we drop it. So this is our feed. So this is the battery limit, of course, and we need to include our test. Remember to leave space up here, and the reason you have to leave space up here is because above every equipment, you have to specify the equipment code or equipment name, and also the specifications of the equipment and everything. Okay, so I think we can have text from general. Let's see, because we are using this app to improvise. Okay, before we go do that, let's continue. Okay, so and the downstream of this would be what? So downstream of this is going to the turbine, like we said. So we need to go get the turbine. Yes, thank you. I want to change it. So we're going to the turbine and we'll probably find it from. It's not supposed to be. It should be on the engine. So we should find turbine on the engine. And yes, we have a turbine on the engines. So yeah. So we have the turbine. So this is like a basic PFD. This is the basic PFD, right? And the turbine should be connected to generator. generator. So we can either use this or we use this. This is a convention we have AC generator, and that's it. So it will be connected to the generator and to generate electricity. Let's go to general and I just need the line. So, and note that this turbine will consume steam. So when it consumes steam, we can decide to use it again, or we can decide what we'll do with the steam after consumption. Okay, so this is our defined battery limit, and so these conventions we have here, these representations we have here are because of the limitation we have for the software we are using. And when we go to, if we use the AutoCAD P&ID, there are other conventions to represent this, to present generators. As for the turbine and the heater, this is general convention. This is general. So for this is also general, but companies during the during the design stage, they define which symbol to use according to the standards. The standards that we already discussed before, the API standards and the ASME standards and all of this, they are very important. So because with these standards, they can come up with which particular symbol to decide on. So this is what we will do in the meeting, all of us, when we are deciding which one, or maybe the owner of the project can decide, okay, this is how we want it if they have an engineering team that's they are interfacing with the project team. Okay, so now we have this already set up. Now one question. Since this is water, right? This is water. And let's go to... We said the steam will have a temperature of 300 degrees Celsius and pressure of 10 bar. Do you think there is something else that we will need? Because we said steam will be 10 bar and 300 degrees Celsius. So if you have any idea, please drop it on the chat box if you have any idea. If you have any idea, drop it on the chat box. What else we think we will need, since we have we want to generate steam at 10 bar and 300 degrees Celsius. This is the steam. This is the specification of the steam that we want to design. Okay, so this is on the PFD. Above the equipment, you always have the equipment name. So for this one, let's call it, let's decide, let's say we're in a project team and what convention do we use to define our heater? So we can decide, we will call all heaters should be E. All heaters should have E. So let's say this is E01 because this is the first heater, right? This is the first heater. The reason we're using E is because E is for exchanger. So we call it E0101. Okay. So I want to put this on the center. not responding. Fine, doesn't matter. So we call it E, right? E01. So what else do we need? We need to write this, we need to specify the name of the equipment apart from the symbol, right? All these things are defined on the design stage. So we call this feed water heater, right? Or feed water boiler. Let's call it boiler. So we have feed water boiler. Okay, I think I should put them with this like this. Feed water boiler, right? So that's the name of the equipment, and this is too big, so I reduce it to maybe 6. Okay, so feed water boiler, right? That's what we called it. And now the mechanical team will specify the design pressure. Okay, I can see a question from Anthony. Yes, go ahead, Anthony.
Yeah, so how did you add the heading?
The heading. Okay, all right. Okay. On the general, you see text box. So the text box has a heading, and then it has the paragraph text. So that's where you get it from general and then text box. General and text box. So that's it. So here you have design pressure. Now, for your information, the design pressure is not just listed like we are listing here. It's not just listed like we are listing here. It has to be a specific design of this heat exchanger. So you go through the heat exchanger design, specify the maximum design pressure and maximum operating temperature according to the materials that will be used for the construction of the heat exchanger. All these are done during the concept stage when different stakeholders come together and make this decision. So they decide, okay, this equipment, what it will handle will be liquid. So what will be in the feed of the heat exchanger will be water, right? And what will be the heat source? This is another discussion open to the design team. So what's going to be the heat source? Because we want to generate steam, it will not make sense to send, let's say, another liquid of high temperature here. It will not make sense to send another liquid of high temperature. And besides, we already said it's a boiler. So what we require is heat from uh, combustion, natural gas. Natural gas. So there will be tubes in this. There will be tubes. So within the tubes will be the water, the feed water, and in the inside the heater, you have these tubes moving around. These tubes coiled inside the heater, and then there will be the flame source where natural gas will be burned. So I don't know if I can give you. You probably already have a pictorial view of imagination of this. So, but this is the representation of it. So, and So in this stage, we'll decide, okay, what kind of material should we use uh, for the tubes, because they will need to withstand very high temperature. Otherwise, the tubes will what? Fail. There will be tube failure. And when we have tube failure, there will be water or steam going uh, the boiler uh, into the boiler combustion chamber. Okay, because the tube and the combustion chamber are not the the the, the components are not mixing. They're not mixing. In the combustion chamber, you have natural gas burning in flames, right? And then in the tube side, you have water coiling through the tubes. And then at the exit, you have what? Steam. So what you have here, you change this label to what? Feed water. And you change this label to steam. So now we can go to general and choose text so that we can specify what we want here. So what we want here is NG, natural gas that will burn. Then at the other side, we'll have what? Flue gas. Because after combustion, you have what? Flue gas. So now we have done this. This should tell you that we have some energy here that we can recover. We can recover heat from here. We can recover some energy from here. So because when you burn the natural gas, it's gonna be hot, and when it's hot, it's gonna convert this to steam. But also the flue gas is gonna be hot also. So we can recover heat from this, and also use it to also heat again, or maybe preheat the feed. So now, excuse me. So now this should open your mind more on how to optimize this facility. We have already decided that though this is the basic equipment we need, but now as we are designing, we're having the discussion, we are beginning to come up with, okay, this will need to, we don't need to waste this heat from combustion. So we need to find a way to recover this heat from combustion and send it back to generate more steam for what the uh, turbine to use to generate electricity. Okay. All right. So now we have established that we have established this. So design pressure at this point, we cannot exactly say what the design pressure will be because we have not done the mechanical design of it. So the mechanical design for this heat exchanger will be required, of which the project team will be responsible for. So and we're going to make an assumption here that the design pressure will be, let's say, remember what we want to, the specification we have is 10 bar for steam. So it means that this should be able to withstand 10 bar pressure, right? So let's say the design pressure, if we require 10 bar of steam, it wouldn't be necessary for us to go to design a facility that will have equipments with pressure of over 60 bars. I mean, except we have future plan to increase uh, the quality of our of steam we want to do, we want to produce. For example, this company is supplying steam to another company, right? The other company doesn't want to take the responsibility of generating their own steam, so they contract steam production to this company now that we are designing a steam plant, right? A steam generation and electrification plant, because the electricity will be used to uh, power some equipment, power the lighting in the facility, power the lighting in the roads and the plants and everything. Okay, so and also there will be a backup generator that will supply power before the startup of the plant. So all these things need to be in consideration, right? So let's say we'll give it a design pressure of let's say 30 bar because we plan to maybe expand in the future, right? And then we have a design temperature of already we are, if we are going to operate at 300 degrees Celsius, so we can design uh, a heat exchanger that can withstand temperatures above that, and we can say let's give it about 500 degrees C. So yeah. So and another assumption we'll be doing here is that because we don't want to fill up this space here, is that this 500 degrees C is for both the combustion chamber and also the tubes, because we need to specify the design temperature for both the uh, the combustion chamber and also the tube side. Okay, so now we have done this. Now also for the turbine, now we need to also uh, repeat the same thing for the turbine. And let's say for turbine, we want to name it, let's say we'll give turbine T01 will be for turbine. Okay, and this is turbine, steam turbine. So this is the steam turbine, and of course we also need to specify its own conditions for operation, because if it will handle this, it should be able to handle whatever thing that is going to receive from whatever material to receive from the from the upstream part of it. So currently we are not receiving any corrosive equipment, so we have no need to use very expensive materials like carbon steel and all of that. So some of these things are sometimes specified what type of material will be used in the for the particular equipment. Okay, so now uh, let's assume that the design pressure and also the design temperature will be the same because it's handling the same fluid. Okay, and yeah, so that's it. Then for here, for the generator, I copy and paste generator. I need to paste this properly so that it won't be too. So okay, so now we have quickly developed a simple PFD for this. Okay, this is for the exhaust steam. Consumed steam will be here. Okay, so I believe this is very easy. I believe this is very, very easy because that's why I chose this, so that we don't go into very complex things. And of course, this is our battery limit. This shows the beginning of the plant. This is the beginning of the plant. Okay. All right. And excuse me. Excuse me. All right. So that's it. And now, if we say that this will run at 30 bar, was it 30 bar? What was our specification? 10 bars, yes. So we decided that we will run this at 10 bars. So what does it mean if this will run at 10 bar? If the feed water will be at 10 bar, what does it mean? Okay, first, something we didn't put, we need to specify the feed conditions. So we need to specify the feed conditions, and that's what we'll do here. So feed water from storage. So if you notice, we didn't need to draw any storage tank or whatever. So this is enough to specify your the battery limit. Okay. So now I choose test again, and then what I want to do here is the conditions of the feed. So the conditions of the feed is that the feed is coming at the pressure of course, water is coming, is pressure of atmospheric pressure, which is 1 bar. So if it's coming at 1 bar and the temperature is, the temperature is 30 degrees. Oh, come on. Okay, so if it's coming at 1 bar and temperature is at 30 degrees, so what does it mean for us? It means that uh, it means we need a pump. We need a pump. We need a pump to raise this thing from 1 bar to 10 bars. Okay, so already we have a heater that will raise this to 300 degrees Celsius, right? So this was what we skipped. So we need what? A pump, right? Do you all agree? To increase the pressure of this from 1 bar to 30 bar, you need a pump. And the reason we need that is because we need to move this fluid from one point to the other. So, so, okay, you want me to change to white background. This is very unfortunate because I am more tilted to the dark side of graphics, and the white side of graphics is very, very bad for my eyesight. So, I don't know if you have a problem with that. Maybe you should just use white on your own. And yes, yes, we need pump to increase the pressure. So we do. So, so can you find the pump? Where will you find the pump from these? Excuse me. Okay, yeah, please manage, Shayima. Sorry, it has to do with my eyesight. So I have to manage it carefully. So, so can you add a pump to your own? And I don't know if you have the opportunity to add picture on the chat box. If you're not able to do that, maybe you take a snapshot of what you already have and send it on the chat box. If you're not able to do that, send it on the WhatsApp group. And please send it in after you have included the pump. So I don't know if you have done that. I will quickly do it on my own as well. Very good question. So what kind of pump will you need? What kind of pump will you need? So what kind of pump do you think we will need here? Because we have different types of pump and for different purposes. Okay, well, centrifugal pump can be used and it is much more suitable for this because this is a small scale operation and um, for turbines you need high pressure steam, so we need pump. Although centrifugal pumps they generate high pressure, they generate high pressure for you, but they are more precise uh, your for continuous flow. Okay, so in this case, it's a question of okay, what do we want to what do we want to achieve here? Do we want to achieve what's the steam rating that we want to achieve? And the steam rating we want to achieve here is around 300. So a centrifugal pump will be better, and just one stage, a single stage centrifugal pump will be okay for this. So, but this is a question of going back to also check costs. Okay, what's the cost of a centrifugal pump, and what do we want to achieve? All these things go take place um, during the discussion phase, during the concept phase. So, which we have not done here. So, for this, we will use a centrifugal pump and one stage, a single stage centrifugal pump, because where we will need much higher pressures. For example, let's say we are looking for above 60 bar, we can have multiple stage of centrifugal pump where the output of this pump one, is feeding pump two. I don't know if you understand. So these cases, you find these cases in the industry. They are very typical in the industry. You see them. You have three-stage pump, four-stage pump, where the output of this pump is feeding the input of another pump. So, and this requires precise control and automation. Otherwise, there will be frequent shutdown. And also, these pumps are also designed to have redundancy. For example, what I mean by redundancy is where you have two pumps, one will be in
Huh?
operation and the other will be on
Is
standby.
it?
Okay, someone unmuted his mic.
Me, I'm there.
Okay,
Congrats.
please, can we all mute our, can we all mute our mics? Okay, yeah. So for this case, we are using a centrifugal pump. And please just send me a screenshot of what you have there. If you have a centrifugal pump in your own, or if you choose to use a positive displacement pump, it's also okay. Both will serve the purpose of steam generation at high pressure steam. So, but you also need to have your the annotation of the equipment right above it, just right above it, immediately above equipment. So if you have your pump here, you should have the annotation of the pump above it. So please send it into the chat box. Send a screenshot into the chat box or WhatsApp. And please give me a minute to take this call while you send it into the chat box.
Yeah, before you go, sir, please, where should we place the pump?
You need to place the pump just immediately after the battery limit. It should be the first equipment before the heater.
Okay.
Okay, are you guys done? I haven't seen anything on the chat box. If you are done, please send the screenshot. Thank you. So I know that we are all following, we're all doing one thing, we're all together. Okay, what is the status? Are we done with it? Okay, it seems it's taking us a bit of time and we cannot afford that time, so
Mr. Nkem, if you are speaking, the mic is muted.
oh, okay. Oh, I so you've not been hearing what I've been saying. Okay, fine. All right, so I can see what you've done, and it's okay, it's cool. So this is basically what your PFD would be. This is your PFD. It has very few information about the instrumentation of the plant, and below it you have the title of it. You have the title below. So I don't want us to waste much time on this. So this is your PFD. And now I want us to quickly go to our DWSIM and try to replicate this. I'm gonna replicate this on the on DWSIM. So, let's open the software. So are we still here? Okay. All right. So now, so let's go and replicate this. So there are okay. This is a typical steam generation and electricity generation plant. However, this one is from biogas, which is just natural gas. It's just that it's from biological, is a biological from biological materials, right? So we have a biogas digester, and then we have a biogas combustor, and then the free gases, which we already showed. This is the what would you call this? What would you call this? What would you call this equipment? You need to drop on the chat box what you would call that equipment. This one here. Are we here? Am I muted? No. Okay, yes, that's the boiler heater. Okay, yeah, it can also be a heat exchanger because it's changing heat from two processes. So, what do we have here? What is this? This is oil. This is oil. This is called oil. Terminal VP1 fluid is oil. This is a very common oil used in the industry. Okay, and then it's being circulated pump. So the oil has uh, uh, it absorbs more heat than the water. Okay, so we heat the oil, and this is the combustion chamber. Then the digester sends in the gas here. The gas is burned. Then the tubes are inside, and then the oil is heated, comes here. Then it exchange heat with this one. Okay, and this is water. And okay, no problem this one. Let's just go ahead and then exchange heat with the water. And the water is steam at this point, and it then goes to the turbine. And the turbine connected to the shaft of a generator generates electricity, right? And then the consumed steam there, yeah, has to go here and then turns to water again, and the cycle continues. So we are going to simulate this now, and just a moment, and we'll pull up the DWSIM. So so you can open yours and let's go ahead and simulate this plant. So now it opens and we have the first page shows up, shows you things about process modeling, whether you want to create or whatever, all of good stuff. So documentation, and if you want to pay them some money, you want to donate, and you can go ahead and do that, buy them a coffee and stuff. So what we're interested in is to create new file. So I want to create or load chemical steady state or dynamic process models. For in this case, we're going to simulate a steady state uh, process, okay, which is the steam generation plant. So the first step, create new model, install. What's the difference between installer package and portable package for. Okay, I'm not sure I know exactly what that means. Package and portable. I think portable should be the package that has just yeah. Need to close this off again and go to the yes. I think the portable package doesn't come with the. There is another software called Cocos or Chemsep. Yeah. So I think the portable package doesn't come with Chemsep for. So if you download installer package, I think you should have all of this, including this Chemsep here. But the truth is that I'm not pretty sure. But either of them, you have DWSIM. Yeah. So either of them, whichever one you choose, you have DWSIM, which is what we are interested in at the moment. Okay, I can see Anthony as a screenshot. Okay, from here, yes, so I see what you say, portable package, installer package. I think what you need to go for is installer package. I think that's what you need to go for because that is also what I have, installer package, which is 278 MB, just slightly larger. So, so I think some people already have it, some of us already have it. Um, So, if you already have it installed, this is the first window you will see. It's very similar to Aspen HISIS, which I also lost the license. I don't have anymore. So this is what I use for uh, educational purposes or to test some things or some process we're developing in the lab. So yeah, this is the first page. You will see the introduction to say welcome to the simulation configuration wizard. And here you select the compounds and property packages and set the system units and configure the specific parameters. So we go to this page and this is where we will select what compound we want to use. I believe you're already familiar with this window here. So here you have all the components that you want to add. For example, if you want to go through some petroleum products, we add the components, the feedstock if you want to do natural gas, methane, ethane, propane, and butane, and whatever on the rest. But here we chose a very simple process. Right? And that is what you just type in water here, and water shows up. You just pick it up, and that's it. Added water. You go to the next page. Now here, this is where you select the thermodynamic property package that you want to use. And in this case, I have to ask you a question. So, what thermodynamic property do you think we should use for this simulation? You can drop it on the chat box. You can drop it in the chat box. And while you're dropping it on the chat box, I will get some water. Just in a minute, I will be back with you to drop it on the chat box and I will see it. Okay, I can see your messages. Thank Robinson. I know this is the most popular by Professor Peng and Robinson. I think developed in Canada. I can't remember which year, but they are two professors of Canadian universities, if I remember the history very well. It's been very popular and very efficient for calculations. So yeah, so you select the thermodynamic property based on what you want to do. Penn Robinson is popular. Yes, yes, yes. So we have the uh, Routledge Kwong, uh, and all the other property packages. This is Swerve, Routledge Kwong, SRK. You must have done all of this in thermodynamics in school, Uniquark, Wilson, and the modified Unifac, Penn Robinson, and all blah blah blah, all the other, and LTL and the rest of them. Then for amines, if you're going to deal with what's it called, scrubbing operations, stripping and absorbing and absorber and stripper operations, right, or processes rather. So in this case, what we want to deal with is water. So the most appropriate uh, excuse me, thermodynamic property package would be steam tables. And the software actually does a recommendation for you and then takes the ones that you can actually use. You can use any of this, but the most recommended would be the one at the top, which is steam tables, IAPWSIF 97. So all you just do is just add it, steam tables. You remember your steam tables in the university, probably when you had exams, your kind of thermodynamics for those who studied chemical engineering and petroleum as well. I think all engineers will have to do thermodynamics at the first and second year. So you probably encountered this. And the steam tables, this is what you have here. You add it and leave the rest as default. Yes, 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 leave it as default because whether it will be solid, vapor, liquid, whatever, do all the calculations. So this is for your phase equilibrium. So leave it as default. And then you click next. And this is where we select the SI unit that we are conversant with. So we are conversant with Kelvin, we're conversant with kilogram per second, and all of that. The one you are more comfortable with. For me, I'm more comfortable with SI engineering because it's in degrees Celsius. I don't have to crack my head to do all the calculation to add plus 273 to 25 uh, to convert from Celsius to Kelvin and all of that. So yes, Enoch, I can see you. Yeah, thank you. Good. So, uh, excuse me. So yeah, so I'm using the SI engineering unit. So if you're not comfortable with it, let's say for example, your design team, you guys decide that you're going to be using uh, turns per hour, turns per hour. I think you are able to change it here. Or maybe this free version doesn't have. Okay, we can change this, but if we clone it, and this is a clone now, so we have SI engineering and then we have SI engineering 10. So for the clone, we should be able to change it to what we want. Let's say we want to make it kilogram per seconds, then we can change to kilogram per seconds as our feed rate, depending on how we want to do it. So, but let's leave it at kilogram per hour. Okay. So, and all of this. So only when you clone it, you can use change it to what you want. If you want to use prefer Pascal, ATM, inch water, inch mercury, and all of that, millimeter mercury, whatever. You have the liberty to change it after you have cloned it, but you will not be able to change the original uh, designed SI unit. So when we do that, then you now click next, and then to ask you some other questions which you just need to skip, just next, 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 and we go to the finish, and we prepare our simulation. So I want us to be pretty fast because we've spent very long time here. So now from your PFD, you have your PFD. on your PFD, we will do our simulation. And another information you need to know is that we need to have the material and energy balance sheet. It's always at the back of the PFD. It's always at the back of the PFD. It's called. It's always at the appendix portion of the PFD. Yeah. So going back to PFD. Yeah. So this will be one of the pages of the document, and then the next page you have some other things, other processes, because what we are focusing on is on the utility. And at the bottom part, we have the title. I don't know if I mentioned that. The title we have the companies, the stakeholders that are involved, the owner company, the project company, and the rest. So it's important to mention it here. But for the purpose of this mentorship program, to give you exposure to it, and then you have you have some industry information where you can step on for your next stage of learning. Okay, so because it's impossible to learn everything with this session. So now let's go to the view. Now, so I'm going to add the material stream where we'll include the feed. We said the feed will be water. So I click this. You just need to click once and we rename this. We call it feed water. And when you type it, you click enter and it changes to feed water. Also, the property package we chose is still here, maintained, not changed. Okay. And the temperature we decided that we're going to use the temperature we want. Temperature of the feed will be 30 degrees, right? This is what we said, 30 degrees. So the reason we are saying 30 degrees is because 25 degrees is room temperature. So we want to simulate the actual environmental temperature, right? Outside, for example, I don't know what the temperature it would be in Nigeria, right? It's probably around 30 something or whatever. So for here, depending on the environment, right? So these are all part of the feed stage during the design concept. The temperature of the environment, average temperature of the environment throughout the year. This is what you put here. But for steady state, we'll choose a static temperature. For dynamic state, it could change to whatever the atmospheric temperature will be. So we are assuming this is 30 degrees, right? And we choose 30 degrees and that's it. So, and of course, remember on your PFD, you have a pump and the pump will be taking the liquid at the water at, this is what? Atmospheric pressure. So to be at atmospheric pressure because it's not being pumped yet. And the flow rate will be 1 kilogram per second, which is 3,600 kilogram per hour. So we leave it like that. So this is the flow rate we want. So we don't want it to be very high. So we have defined our feed water. And then the next thing we will go to is the pressure changers where you will find pumps, compressors, and the rest of them. So we choose pump and yeah, and you choose pump, the rest of the stream gets connected automatically, right? So, and this is the energy requirement of the pump. At this moment is 0 kilowatts because we have not solved this calculation yet. So, now the next equipment on our PFD, we have the heater, right? So we will go to heat exchangers and we'll find heater. We don't want to use heat exchanger, we want to use heater, okay? So we use the heater. So this is the heater and so for now, we want to focus on just steam generation. Let's just generate steam alone and see what will happen. Okay. So now, if you just take your mouse towards this, you find the, you'll see feed water compounds amount basis molar fraction, the mole fractions of the water. You see compound, phases, and you see overall, vapor, liquid 1, liquid 2, solid. And that's because we left we left the phase settings to be vapor, solid, liquid. So if there is any at any point in the simulation we begin to have solid freezing, you will see solid will change to 1. The fraction, the mole fraction of solid will change to 1 on this table you see here, right? And then you see the feed water, material stream, temperature 30 degrees, pressure, and the rest of them. So now that's it. So for the pump, when you hover around the pump, you won't see anything because it's still highlighted in red. We have not specified anything for the pump yet. So we only specified for the feed water, and that's why we have it in blue because it's solved. So actually, while you put your add component, this software actually does the solving. You don't even need to click solve. The moment you click a component, it solves that part before going to the next one. So it's actually good and enough for educational purposes. So now we said we're going to generate steam first before we go to generation of electricity, right? So now let's go to the pump and specify. So let's call it pump 1. Let's leave it at pump 1. It's okay. We see status not calculated because it's still red. It's not calculated. And if we go here, we'll see status here is calculated, and it shows you the date and the time it was calculated, right? All right. So now let's go back to the pump and yeah. So the inlet stream of the pump is feed water. Of course, if you want to change it, you can change it, but we're not changing it because we want to feed water. And the output stream is 3, of course, which will change to steam. So we'll rename it to steam, but not now. Only when we click on the stream, then we can change it. So now we want to choose what we want to specify. So we are able to specify either the outlet pressure, the power requirement, the energy stream, the performance curve, but what we want to specify is the outlet pressure, right? So on the outlet pressure, we say we want it to be 10 bar. We choose 10 bar, and we can select the efficiency of the pump. Of course, there's no pump that will be 100% efficient, but let's assume that the pump efficiency is 75%, right? If it's 75%, then we leave it like that since it's 75 here. So now we have the pump at 75. I think I have error in my software because this is not supposed to be here. This is blocking the view. Okay, I'm going to save this and close it and open again. So project review. I will close it and open again. Yeah, I will close the entire application because I think I have an error. Okay, so opening the file. Okay, so the error is cleared. Okay, so where were we? We specified the pump. So we added the output condition of the pump, which we wanted to be 10 bar. If you look at the table, we still have liquid phase. Overall is 1 and it's still in liquid phase. Fraction is in liquid phase, right? And the material stream we see 30 degrees, the same temperature. There's a slight increase in the temperature here because of pumping, friction and between the liquid and the pipe. So of course the flow rate still remains the same, and the pressure has increased to 10 bar because we specified 10 bar. So what was missing was the energy requirement. So this will require 1.2 kilowatts. So already the process engineers have noted, okay, we will require a 1.2 kilowatt pump to be able to move this fluid uh, for a momentum transfer of this fluid from here to here, from the storage to from the feed water storage to the inlet of the heater. So now the heater now, this is where we require energy for the heater, and it will be natural gas. But because of this simulation, we are only able to specify for electrical heaters. So we're not able to specify for natural gas. So uh, we're going to choose the outlet temperature. And with the outlet temperature we chose was no, outlet temperature. Either you use temperature change, of which the initial temperature was 30 degrees, and you can add 270 to it, and it becomes what 300. So if we add 270 here to 70, then three we will have 300 degrees at the outlets, right? Either you do that or you go to outlet temperature and you just choose 300, and then that becomes the outlet temperature. So either way works. So the moment you do that, it solves the calculation, and then you have the energy requirement for this. However, it's given in kilowatts. So this is because um this is because the heat exchanger we have in this software, in this free version we are using, is electrical. So we have the values in electrical. Otherwise, it would be in BTU, British Thermal Units. British thermal units. That will be the heat rating of the natural gas, the heating value of the natural gas or the gas or whatever fuel we'll be burning. Because this is not this is not an electric heater, but however, for simulation purposes, we can use it to rate how much energy we will use to generate steam of 300 degrees Celsius. So with this, we have already generated our steam, and now we can supply this steam to whatever company that requires our steam. So this is the utility plant. So if you look at this, it doesn't have the valves, it doesn't have whatever other things because we don't really need it here. Because what we want to do is to get the energy requirements, how much energy, how much fuel we'll burn. But then this is giving us how much electrical energy we need to power this heater to be able to generate 300 degrees Celsius. Okay, so now let's go ahead and generate um, electricity. So to generate electricity, we said, or rather we have in our PFD that we already developed, that we will need a turbine. So, and turbine is a pressure changer. Yes, it changes pressure and then converts it to some form of energy. So we take a turbine, which is an expander, right? The reason it's called expander here is because it will go from a higher pressure to a lower pressure. So, so we have the turbine here. So the turbine is taking temperature at 300 degrees Celsius, right? And one observation, something to observe. When what do you notice here? This table here, at the table at the top, it has the phases. What's the mole fraction? The molar fraction we see here is on the liquid phase. And after the heater, we now have the molar fraction on the vapor phase because it's now at 300 degrees Celsius and 10 bar. So we now have every liquid has been converted to vapor, right? So that's why we have now one, the total fraction is now one and is in vapor, right? So there are no two phases, and we don't need two phases in the turbine. We only need one phase, which is vapor in the turbine. So now we want to generate electricity, but also as we are doing this, we are basically designing our a full Rankine cycle. That's what we're doing now, because when we have the turbine has to consume the energy, and then it's the when it consumes the steam becomes water. The steam reduces, the temperature of the steam reduces, and then we need to condense the steam to water and send it as a pump and goes back to the feed again, and then it continues to recycle because we're not going to waste the water. Okay, so what we're going to do is that this output here is going to be uh, also steam or water. We don't know, but we need to figure out what is going to be at the end, right? So now this is pump. Okay. So now this is the expander, right? So we have an outlet pressure. We didn't specify anything. We didn't specify anything yet, but we can see an outlet pressure of 1 bar, 1.10 bar. So the software is trying to tell us that once it takes this at 10 bar, at the output we are going to expect 1 bar. So what we'll do, let's just click solve. Now we solved it because we don't need to specify anything here, because whatever we feed the turbine is going to work with it is the working fluid, just like we have here is the working fluid, right? So it will consume it, and at the outlet the temperature will drop, and we still have it at vapor because why? We have 114 degrees Celsius at 1 bar. That's atmospheric condition, water boils at 100 degrees. So at 114, we still have steam. Okay. Except this pressure drops much lower. So then we'll probably have two phases at this point, right? Okay. So now we have steam at this outlet. We still have steam at this outlet. So how do we recover all that we have? We need to recover this steam. We need to make use of this steam, and either we use this steam to supply other utility for other utility, probably um, sending it back to the feed, but not at the feed water, but probably at the inlet of the heater, right? So now, how do we go ahead now to optimize this operation? Because we are seeing that we are generating approximately 346 kilowatts of energy, and it is dependent on how much steam that we are inputting in the turbine. So if we generate more steam and the turbine is able to take in more steam, remember the design conditions that you specified was 500 degrees. So that means we can ramp up to approximately 500, or we can go to 450. So so that we can optimize electricity generation. So I want you to tell me what other equipment we can use to optimize this plant that we have just simulated. Drop it on the chat box. Are we here? I hope we are awake and not sleeping. I know this should be 10:41 and it's 11:41 here. Okay, Blessing Ben, please go ahead.
So sorry, sir. Please can you come and give me the question? Sorry.
Okay, what can we do to optimize this? Now uh we have taken exactly what we have from our PFD and we have put it in, we have simulated it, and this is what we have. So how can we further optimize this? And also, this part is showing you what has been generated. This software does not show you the part of the generator, right? But it shows you what has been generated. This is the generator part. So this is a representation of the generator part, and this is what the generator has generated for you. Okay, so this is the energy stream. If we click on this, we'll see the conditions. It's operating at 75% adiabatic efficiency, and let's see, energy generated, power generated 346 kilowatts. That's what it says generated. So uh, how can we optimize steam generation or electricity generation? What do we do? Remember, we are process engineers and we are trying to develop a system that we are going to
Okay.
use. Okay, go ahead, Abuchi.
All right. Since the electricity has been generated, the the outlet steam, I think it should be condensed and recycled back as our feedstock.
Okay, thank you. So we need a condenser. And a condenser, where will we find condenser? Pressure changers, separators, mixers, exchangers, reactors. Where do you find the condenser? What type of equipment is a condenser? Where do you classify condenser?
It's still a heat exchanger, I think.
Yes,
Sorry.
it is. It is a heat exchanger. So we either pick heat exchanger or we pick cooler. So it depends on which model. This is a simpler and this is a more rigorous heat exchanger model. So let's choose the cooler and we have it here. So let's rename this to turbine. So we have turbine and then let's rename this to condenser. So we have turbine and we have condenser. Okay. And at this point we have 114 degrees Celsius, right? And now if we want to condense this, what will be the specification to give the condenser? Because since we want to recycle the condenser uh, product,
Sorry, do you mean in terms of temperature?
yes, you actually choose the simplest parameter to converge your model, of which it will be temperature, your outlet temperature. That's what we want. So you specify the outlet temperature and then the model computes the rest for you. And the outlet temperature we want to give this would be what? What do you think it would be? Since we want to recycle it.
30 degrees Celsius.
Yes, it can be 30 degrees Celsius. So we have outlet temperature, 30 degrees. So now we have it 30 degrees Celsius. So the phase is liquid phase because it's been condensed from vapor to liquid at this point. Okay. So now there are other things we can actually do to optimize this, and First, we have a lot of steam here, 114, that we are condensing. So we are wasting a lot of energy here. There's something we can actually do. We can tap from this steam and then recycle it to the feed of the heater. So if we would do that, excuse me, if we will do that, we need to break this and take a tap out and feed it back to the heater. And how do we do that? We'll see how we do that. Okay, first I need to change this to steam. We'll change this to steam. So it's the steam. Let's call it superheating steam. Let's just call it MS steam. Yeah, medium steam and then the low pressure steam. This is low pressure steam. It's still steam but at a lower pressure. It's high pressure steam. Higher pressure steam. We have a HP steam, MS steam, and then LS steam. This is the usual convention in the industry. Some companies can change it to whatever they want. So this is what I'm using LS steam here. Low pressure steam. So low pressure steam as a utility is still useful in the plant, and you can also save cost from low pressure steam by are we still here? Okay. So moment. Yeah. Okay. So now let's recycle low pressure steam, and the way we will do it is by we need to break up the steam, and the way to do it with this is by we can use a mixer to do it, or a stream splitter rather. I use a stream splitter. So let's break up this part. Disconnect from where is it connected? It's connected to condenser. So let's disconnect from the condenser. So it's disconnected now. So let's add. Okay, just a moment. So let's add stream splitter. So this is the stream splitter, and one stream will be the recycle to what's it called? The heater. Yes, one stream will be recycled to the heater, and then the other stream will be to the condenser. So let's connect this one to the condenser, and we can do that by going to connections, and downstream we will choose condenser. So we choose condenser and then it connects. So it's now connected to the condenser. Okay, then this stream we need to recycle to the heater. So we will need a mixer here. So we need to also disconnect this stream. So uh, let's disconnect the heater. So we disconnect the heater, and what we will need here for this software, we cannot connect directly. So we need to use logic blocks. Excuse me. And these logic blocks will give us a recycle block. This is the only way we are able to use two material streams, or we can split streams or mix recycle streams. So if we use this, okay, I chose the wrong item, so I will delete. So where is it? Yes, recycle block. Yes, recycle block. So recycle block, and it already went directly. I need to disconnect it from here because I don't want it to be here. So I disconnect it from the pump. Okay, I have done a lot of things right now. So I'm going to delete this. Just follow me. I will delete this again because I made a mistake. And we'll delete this. So I will add the recycle block again. There's flow shift. Yeah, the recycle block. Yeah. So I want it to be standalone. And I will go back and add a mix at this point because I want. Okay, just follow me. Because of the positions, they are so close to each other. It's just picking up the. It's automatically picking up the strings and connecting them, which I do not want. I want to connect them manually. Okay, so now I have this recycle string, right? So we already connected the part going to the condenser and we split the string to go to the input of the, what's it called again? Heater. Yeah, of the heater. So now, I need the, mixer. So I will add the mixer here so that I don't want it, because I don't want it to start connecting automatically. So now, um, I will connect this mixer. What I want to do is I want to take the mixer and take one stream from the pump and one other stream from the, uh, downstream of the turbine, right? That's what we want to do here. Okay. The reason I took this is a logic solver. This logic solver will help the model to recognize that it's a recycle. Okay. Without it, we'll not be able to solve this model. Okay. So first, I'm going to take this stream and I will connect. Let's push this forward. I will go to connections and the upstream will be from pump one, right? Okay, I chose material stream 12. I want it for 13. Yeah, I want it for 13. For 13, I'm going to make the upstream to be pump one. I go to connections. Upstream will be pump one. No, sorry, I chose the wrong one. Pump one, yes. So now I have it connected. Okay. Now the other stream I want is the recycle stream, right? So for the recycle stream, I want 12 to go to 7, right? 7 will be feeding 12. And then first, let me connect 14 to the heater so it becomes very clear. So I will move all of this. I'm going to move this backwards so that we have a very clear chart. I'll move this backwards. This is very sensitive. I'll move this backwards. So, and I will place this here. I need to close this down. Okay, so now I need to connect 14 to the heater. So I will click on the stream 14 and go to connections, and downstream will be HT1, which is the heater, and then it's connected. Okay, so everything is running everywhere. So later we'll need to rearrange the structure so it will look much better. So now what I need to do now is to connect the split from the steam, because we want to maximize steam. So we want to take this steam 114 degrees here, I want to send it back to the heater. Okay, so to do that, first let me try to connect 7 to 12. Ideally, we should connect 7 to 12, but if we try it now, we're going to see it's not going to work. So if we try to connect, where is it again? Oh yeah. So now I'm going to try to put the upstream to be 7. It will not work. It's going to generate warning. Caught on hardwood exception. The connection is not allowed. And the reason is because the model is not able to detect such recycled streams without this logic solver. So this logic solver is to help the model to be able to recognize that this is a recycled stream. So what will happen is that I will delete this stream. I will delete this stream. And I will delete this stream also, stream 7, because the logic solver comes with a stream already. So 10 will be the one feeding the logic solver, and 11 will be the one going to the recycle. So now I'm going to specify stream 10, and stream 10 will be coming from split 1. Split 1. So I'll click on 10, and then I'll go to connections. The upstream will be split 1. And now we've specified it. And then the downstream will be, downstream of 11 will be, because we already have one stream from the mixer going to the heater. So downstream will be to the mixer 1. So I'm going to click exactly. Thank you very much, Anthony. So connection downstream will be to 1. And yes, we have it. So we need to arrange this to look like proper. Let's tidy up this thing. And yes, this is very sensitive. We're using free version, so yeah. So this will be clearer for us to see what we are doing. Yeah, this is much clearer. So there's too much space here. Move this a bit. And yes, the logic solver is there. And yeah, so we have it. Okay. And are we missing anything? Is there something we are missing? Let's see. For the condenser, we have 30 degrees, so we can feed it back to the pump. We can feed it back to the pump and recycle. So the conditions at the output should be the same with the conditions at the input, so which we already have here, 30 degrees, 1 bar, and then 3,600 kilograms per hour and all that. Okay, so that's it. And we can actually use, for this feed, we can also use a mixer and then specify feed water. Okay, let's do that actually. So I'm going to delete the feed as well. So this will, okay, this will probably destroy the simulation, but it's fine. We can re-specify again. First, let me click no. And what I want to do is I want to add a mixer, and then one stream will be from the output of this condenser, and then the other stream will be the feed water, right? The raw feed water. So let's do it this way. I will add, okay, first let's solve this one. Let's solve this and see if there's anything we are going to specify. Let's solve this. So we have this solved, and now the turbine is not generating anything. And why is that? We need to find out why it's not generating anything. We have pressure at So let's see. We have steam here, we still have steam here, and down here we have vapor, yes, 300 degrees Celsius. Okay, that's the problem now. So we have the turbine is not consuming any energy. It's not consuming energy. The upstream is 300 and the downstream is also 300. So we need to re-specify this because of the changes that we have done. So now we need to, where is the steam? So we are basically just wasting energy. The turbine is just no offline. It's basically offline. So let's specify energy pressure decrease. And pressure decrease would be to, okay, we already have pressure outlet here, which is atmospheric condition. Let's see. So pressure outlet is atmospheric condition, and mass flow changed. Let's see where the error is coming from, because we had a lot of modifications. Okay. Okay, because we had to feed, let's see, temperature here 13 degrees, and then we had a mixture. So something is not right here. Let's see. Okay, now I have this error here again. So guys, are you following? Are you with me? Okay, thank you. So I'm going to restart this again. I'm going to save this and I will restart it. Because I have these errors here. And, okay, so load the previous file. Yes, we have it. And another thing is always good to save different versions of your models. So which was a mistake that I did. I saved above the other one that I already did, so I don't have the previous, excuse me, version. So it's good practice to have version control. And for those who are studying software engineering, I'm sure you already know this. We use GitHub to for your version control. So you do your manual version control here, have different versions of your files of your models. So which was a mistake I already did. I already saved on the previous one. So we don't have the previous version. So we have to fix this one. Now let's find where the error is coming from, because our turbine is currently not uh is not generating electricity. It's not generating energy. The same temperature of the steam goes through to the outlets. When I generated this model before, I didn't have this issue, but now I have this issue live in the class, so we have to figure it out. And let me see. Okay, 30 degrees. And here we have 30 degrees. 10 bar pump. Okay, and we have 300 degrees. Okay, we shouldn't be sending 300 degrees back to the recycle. So the problem is somewhere around here. So we have 300 degrees going to the recycle. No energy generated. No energy generated. So this feed is wrong because we should have 30 here. Okay, we have 30 here. We have 271 here. One bar. Probably because of the recycle. And recycle mixing with 30 degrees, the temperature will drop from 300. So, but we don't need 300 here. We're going backwards. We have 300 point. This is okay. So our problem is here. Our problem is the turbine. So let's see what we can specify to fix this problem. Now we have the rotation speed 1500 RPM and outlet pressure is correct. Outlet pressure is okay. The efficiency is okay. That's 75%. And let's see. Power generated. Okay. I think in this case now, because we have added new components and modified it a lot, we need to add power, the power we want to generate, and let it solve the rest of the system. And this will decide what we are going to specify for the rest of the equipment. Of course, we can still adjust it and see the effect of these changes we're going to do. So let's say we're going to generate approximately, we had 356 kilowatts, I think, the previous one. So let's say 350 kilowatts energy generated. Okay. Please inside recycle blocks where needed. So we have a recycle block that we have not included. So that's the reason we have this problem. So we have recycle block here in the right place. So we need one more recycle block. And where will that be? Okay, so let's just go ahead and put the recycle for the condenser. So it could be the reason why it's refused to solve because it's detecting a problem somewhere. So this could be the problem. So let's add the recycle block back to the feed, and I will take a mixer here, and I'll put the mixer at this point, and one of the streams from the condenser will be, because this is automatically what we're doing is a Rankine cycle, right? So let's complete the cycle. Where is it? So let's complete the cycle and see if we'll think in the previous model that I created, the cycle was complete. So that's probably the problem we have. And okay, I can see that my turbine has lost its energy connection. Okay, a lot of problems here. Okay, so we have a problem here. This has been disconnected from the turbine. So this is coming from the turbine already occupied. So now that's a problem. Oh, outlet connection. The inlet is turbine. Okay, still connected. So let's add the mixer. So we added the mixer and we need to put a logic solver. So let's get the logic solver, logical blocks, and I'm going to add it here so I don't want it to connect. And I will take the downstream to, let's rename this to, let's rename the feed water to, yeah, let's leave it at feed water. And let's rename stream 12 to raw feed water. Raw feed water. Raw feed water. And let's delete this one because we will use a logic solver. We'll use the recycle stream for it. So the input, so we want to send the output 17 will go to the mix 2. Output connections and mix 2. We have mix 2. So let's label it like this. And yeah, everything is running. Help us. Alright, so then 8. So let's remove 8. Let me see. Okay, 8 already have this. Okay, let's remove 16. Let's remove 16 and let's put 8 to it. So let's make R2 downstream to be R2. Yes. So okay, so we have it. Now let's solve and see if it will fix itself. So please insert recycle blocks where needed. So we still have the same error. So this didn't fix it. So where is our problem coming from? Alright, process engineers, your inputs are needed here. Bring your inputs. Let's find where we have the error coming from. Bring your suggestions and let's figure it out. So things like this can happen, and when it happens, you have a headache, and everybody is wondering, okay, what's going on here? But then, as teams, we put heads together and solve it and fix the issues. So whatever thing, whatever thing that comes to your mind, just throw that input out there, and let's see if that will help us to fix this issue. Basically, our issue is coming from this point, and there is a recycle block that we need. The turbine and heater outlets are mixed up. They are mixed up. Are they? Where? Where is the turbine? Turbine outlet. Yes. And turbine and heater outlets.
Sorry, let me use my mic. That yellow
Okay.
stove,
Mhm.
that yellow stove at E2 and E3. I think one should be coming up from top and one should be coming up from heater. I don't
At
know.
at E what?
E2 and E3 that is coming out from. I think one is coming out from the heater, and one is coming out from the top. I don't really understand how it can got
Okay.
mixed up.
Okay. E2. Okay,
Oh,
I see where the
I
problem is. Yes, yes, yes. You're right. You're right. So I think I probably misclicked something because this E2 is for the heater, and now I see it's connected to the turbine. So there's a problem here. Thank you for that. So this is the problem. So output, the energy stream shouldn't go. So I need to disconnect this. I need to disconnect. Yeah, yeah, yeah. Okay, so this has been disconnected. Thank you very much. Thank you very much. So this must have happened when we had that error before I did the restart, and this should go to the turbine inlet. Should go inlet energy stream. Sorry, this should be outlet energy stream. Should be the turbine. Occupied already. Why? No, it's not occupied. Okay, let me disconnect it first and see. Okay, occupied already. Oh, there's a problem here. Okay, let me solve and see. Okay, now there's a problem here because the energy stream has disconnected and it's unable to connect now. Okay, so guys, we have generated an error for ourselves and now we don't have the previous script to fall back to. But one thing I can do here is to open this stream. Okay, now this is exactly the same plant. No, not this one. Which recycle stream. It's the same plant, but the other one without the recycle, and this one with the recycle stream. This is exactly the same plant, and because of time and the problem we have already generated for ourselves in the other one. So this is exactly what we had there in the previous one. I can see someone drop a message in the chat box. He said, "What? Is it possible to remove the turbine and introduce a fresh one that will automatically come this energy line?" Okay, we can do that. We can do that. So, but before we do that, to solve it and get exactly what we have here, this is an already solved one, which I did before we started this session. So this is a solved one, and then our turbine is generating electricity at 350 kilowatts. So this is basically just a small lab scale plant, and it's consuming 3,670 kilowatts of energy here at the heater and generating 250 kilowatts. So, but this could be increased when we alter some of the parameters. For example, the efficiency we have here is 75%. We can make it to be 85, and we'll have some changes. And let's solve it and see. Now I generated another error from here again. I'm glad I have the previous version saved. Function does not accept floating point. Okay, found the same error. So there's probably an error somewhere that's causing this problem that we have here. Because let's go back to the previous one, project review. Okay, this was it, right? Yeah. Yeah, so this is it. This is before we added a recycled stream. Yeah, so here I think everything is okay in this point. Let's solve and see. This was where we had the issue. We have two errors. Reach the maximum number of iterations without conversion. I think this is probably because we are using free version, and then this is not able to continue any operation, because this is really strange, because everything is okay. Everything seems right. Everything seems right. And yes, condenser outlet is 30. The split. Maximum number of iterations is 50. So I guess we have done 50 iterations today with this software, and now we are not able to proceed because this is the error we are getting right now. Let me see if I can add a new recycle block, if that will change. Let's see, budget block, recycle. We will remove this one. So I'm going to make the inlets to be 10, is that correct? Yes. And the outlet to be 11. Let's see, we'll have the same problem. Maximum number of iterations, 50. Let's solve it and see. So this seems to not have errors. Open panel info. So we still have the same error, still have the same problem. So we have exhausted the maximum use of this software, of this free version today. So what will you do if you have your own model and you already have this in place? Try to solve it and send me a screenshot of what you have as your energy generated. So without changing anything, without using exactly what we used to have around 300 and something here, because that's exactly what we have from the previously generated, um, the previously built model. The model had exactly the same model, same specifications, everything the same, nothing different. And so you should have this. Where is it? Yeah, you should have this 350 kilowatts. So this is where we will end the lesson. We have spent spent uh, time on this, and it should give you like your basic basic knowledge of your preparation for your plant design and all the stakeholders that are involved, your basic uh, design basis, specifying your design basis, and developing your PFD. Of course, the PFD is not the complete information, because it requires that you will have to do some other some stakeholders are required to do the mechanical design specification and the material specification. Well, all this will be done in a project, and but so far we have developed this, and then we decided to go from this to the simulation of, this is what we are able to do as process engineers, simulation, and try to see what we can alter, whether we'll be making profit from this. So we can go to the mass balance, and we can see the energy consumption, because here we want to generate electricity. We can see what we are consuming and what we are generating. So that's it. So for this plant, we have a lot of optimization to do for this plant. So we build the model, but we have a lot of optimization to do for this plant because we have to do energy consumption generation at the negative. So this plant is, although it's generating electricity, we are consuming a lot of energy, especially here in the heater. We're consuming a lot of energy. So we need to come up with other things we need to do to maximize this process. Already we added a recycle stream. We added a recycle stream, but it doesn't seem to help much. And we also need to do other things. And these are the things you have to go back and sit down and discuss in the project team and come up with the way to optimize this part. So that's it. Because it's not just to develop the plan, to model it. It needs to be profitable at the end of the day. It needs to have positive at the end of the day. So this is where we will end our session, and that will be the final, because we have compressed everything into this session, and that's why we had to spend more hours to go through everything. So we have gone through the basics of entering into the process engineering footwear. So this is how you can start. Learn the standards, the code, the regulations, and of course, you need to know the project lifecycle, those who are involved. We've learned the differences in PFD and the P&ID, and the process of developing them, the basic knowledge of developing them, and of course the project lifecycle, those who will be involved in the project. At least you can see at this point there are some things we are not able to do on the PFD because we don't have everyone who is involved in all the people who should be involved. Of course, the environmental engineer, process consultant, mechanical engineer as well, who will be there, who is also a process engineer as well. So all of these will be there because one single engineer cannot develop the entire system. So this will be the conclusion of our this mentorship session, and are there questions you have? If you have questions, I think this point you have to throw them up on. You have to drop them on the chat because this is past my sleep time. This is 12:30 right now. I have to be up early in the morning and go about my business. So yeah, I hope this was resourceful for you. And this is not your full toolkit. You need to still read and read and read. You need to read textbooks. You need to read your Coulson and Richardson. You need a lot of tests. Oh, of course, a lot of recommendations. Textbook I can recommend for you, and some I can drop for you to read. The truth is that right now you're a student. You have the opportunity to read as much as possible. You have to read very hard. Not just read. You have to read very hard. You have to really sit up. You have to go through the pain, and after the pain comes the gain, so that you prepare yourself. And is there a practice manual set of practical questions you can exercise on? You'll find these things, I think, in Coulson and Richardson, the volumes of Coulson and Richardson. I think I have from volume 1 to 6, so I can share them with you, and you take them. They are not easy to read because they are voluminous that big, but if you have the drive, you read them. They are books you keep with yourself to keep reading even when you are in the industry. I still read them off till today. In fact, I had to go through some things in the textbooks and prepare this lesson. So yes, so that's it. I will drop you the textbook PDF on WhatsApp because after this meeting, I think this nothing will be able, you won't be able to get any material from here when this meeting ends. So you get them on WhatsApp. So yeah, and your questions, please drop them on WhatsApp and I will get them from there. I would have created a form for you to drop the questions, but just use the WhatsApp and then we'll respond there. So for now, good night, and I'll drop you the textbooks later, probably tomorrow. And, yeah, so capstone projects to engage in. Okay, that will be dropped also in the WhatsApp group, not tonight. It will be, you will get them in the WhatsApp group. Okay, so we'll liaise with the organizers. That's it. So good night, and my email address. I think it's better to contact me on LinkedIn. Yeah, better to contact me on LinkedIn. Yeah. So if you have my LinkedIn, just put my name. You can just. And if I do not, yes, this will be the last meeting. Yeah, that's why we have to spend this much time. And if you're not able to, if I don't see your request on LinkedIn, just um drop a message on the WhatsApp group that, oh, okay, you sent a request on LinkedIn, and I will see to it. So I close the curtain here, and good night to you all. And please have a wonderful night's rest. Mm. So over to you, moderators of the meeting. Over to you. So I will be leaving, so you can take control.
All right, thank you very much, sir. I really appreciate your time with us. One last thing before we go. So, sir, please can you help us with your LinkedIn profile? I don't know whether the full name or the link, something like that.
Okay, I just dropped the link on the chat.
All right, thank you very much, sir.
Okay, you're welcome.
Okay, sir, we'll do it to connect and we'll try to be in touch even after this mentorship section. Thank you very much, sir.
You're welcome, no problem.
So everyone, this is a wrap for the mentorship section. Please let's do well to appreciate our mentor and let's have a great night. Okay, sir. Thank you, sir.
Thank you, sir. Good night, sir.